seen again uniform law of large numbers, stability and robustness, and now we're going to see an information theoretic perspective. This is after a recent paper by Dan Russo and Drew from 2015 or 2016, I don't remember. 2016, and there is no H. What's the name of the paper? What's the name of the paper? I don't know. Sorry. But if you go on Dan Russo's webpage, you will find it. Okay, so the insight is the following. So the less the algorithm memorize the data, the better it will generate. Okay, so of course, imagine just an algorithm that doesn't look at the data and output something. Well, its empirical performance is going to be the same as its performance at test time. And more generally, if you're trying to look at the data but not too closely, then you will generalize. That's the conclusion. So by memorization, what we really mean is how much information of the data remains in the hypothesis. Okay? So to put it differently, how much information of the data S is contained in H bar S. If there is a lot of information of S which is contained in H bar S, then we are worried that it might not generalize. Okay, so to have a mathematical formalization of this information notion, well, we're going to use information theory. Okay, so I'm going to just give you a few very basic reminders of information theory. Reminders of information theory. Okay, so you all know what is the entropy. So the entropy of a distribution is just, so I'm going to use information theoretic notation also. So P, this is a distribution on some finite set. And let's say capital I. And what is this? This is minus the sum for I in capital I of P of I log P of I. Okay, and you remember the way to interpret this is that you have a channel which is producing symbols, okay, and it's producing symbols IIT from this distribution P. Okay, so you have this channel P, and what it's giving you, it's giving you symbols. Okay. So you have I, which is sampled from P, and what you want is to have a code for this, to have minimal length, minimal expected length. Okay. So if you have a word I, you can encode it with log 1 over pi bits, and then if you do that, your expected length is exactly minus the sum of pi log pi. Okay, and this is the best you can do, meaning that for very likely words, you want to have a small length, and for unlikely words, you're okay to have a longer length. Okay, if there is some word that appear over and over again, you want to give it a very short description. Okay, that's the notion of entropy. Okay, something important for us is going to be the conditional entropy. So the entropy of x conditionally on y. What is this thing? The entropy of x x conditionally on y is just the following. It's minus the sum of let's say p of xy log p of x given y. Okay. So this, if you want, the way to interpret it is now when you encode x, you might know what is y. So you have the information of what is y, and then you can encode x. So this tells you how much your entropy, this is always smaller than the entropy of x. And the smaller this is, the more information there is in x about y. So the notion of mutual information is equal to the entropy of x minus the entropy of x given y. Now this is clear? Okay, so this is a notion of information. This is the notion of the information that there is between x and y. Now, it's not obvious from this formula that this quantity is symmetric with respect to x. Let me just show you that this is symmetric and give another interpretation. So to do this, remember what is the relative entropy. So the relative entropy between P and Q, this is nothing but the sum of, let's say, P of I log P of I over Q of I. And this has an order. P and Q are not the same thing. Okay, so the interpretation of this is really that this is the sum of P of I log 1 over Q of I minus the sum of P of I log 1 over P of I. Okay, you see what is the relative entropy? The relative entropy is that you have a channel which is producing symbols according to P. The best way to code this channel would be to use a code book that is defined using P. Then the expected length would be sum of Pi log 1 over Pi. This would be the expected length of your code word to encode a channel producing elements from P. But now what you're saying is I'm producing from P, but I'm going to encode according to Q. Okay, so this anchors some regret, some loss. Okay, so here the truth is P, but I'm using Q. So this is, you can think this is price to pay for thinking the word is Q, when in fact it is P. Okay, this is the notion of relative entropy. It's some kind of notion of distance. Okay, if this is small, then it means okay, the word was P and you use Q, but Q was not so different from P in this sense of relative entropy. Okay, so now let's do some calculation here. So what is this? Okay, I can sum over all P of x, y, and then what do I get? So for the entropy of x, I will get log P of Px. So I get log 1 over Px minus the sum of P of xy log 1 over P of x given 1. Okay, which is the same thing as the sum over P of xy of log P of x given y over P of x. Which is the same thing as the sum of P of xy log And now I'm just going to write this as, let me see, P of xy over P of x times P of y. You see, P of xy over Py is exactly P of x given y. And now I see a relative entropy. This is the relative entropy between the joint distribution over x and y and a product version. Okay, so this is the relative entropy between P of xy, okay, the real joint distribution, and the decoupled version, P of x times P of y. Okay, so this has a very, very, very clear intuition behind it. Okay. You have pairs x, y, input, outputs, whatever. They are related to each other. There is some dependencies between them. That's the truth of the world. The world is like this. X and y are not independent. But now I'm going to act as if x and y were independent. How much do I pay for believing that x and y are independent while in fact they are dependent? That's exactly what the mutual information is telling us. Okay, so again, this was the mutual information. This is the mutual information. It's a drop in entropy, but you can also see it now as the price to believe that x and y are independent. So you want to believe this, but it's not true, but you believe it, how much do you pay? Okay, that's the mutual information. Okay, any question on those reminders? Yeah.
Why is the first term pxi and not px?
This is px, the first term, you're right, I should have written px, but you see the sum over xy of pxy, say f of x, I can sum out the y, and when I sum out the y, it gives me 1. So this is equal to the sum over x of p of x, f of x. Okay, so that's what I used. If you want, I can marginalize over y, and okay. Yeah. Any other questions? This was a good question. Okay, so let me now tell you a beautiful lemma. So this is the key technical argument in Rousseau and Andrew. The intuition, by the way, why this is going to be useful is for us. Remember, let me just to see where we're going. Remember, what do we want? We care about the generalization, right? Which is, let's say, the expectation of the loss of h bar s on the fresh sample z, compared to the expectation of L of h bar s on a random element zi.
Can you take another pen?
Yes. Yeah. Let me explain this, just to see where we're going. Black is fine, right?
Yeah.
So, where are we going? Okay, so we want, following, we care about the expectation of the loss of h bar on s z, when z is sampled from mu, and we want to compare it to the expectation when z is sampled uniformly from S, the data set, of L of h bar S. Okay. So you see, here, these are independent. And here they are dependent. Okay? So when you are at test time, the sample on which you are evaluating is independent of your hypothesis. Okay, that's the test time loss. You have independent. But at training, you're evaluating on a sample from your data set, but you're also training on the data set. So there is a dependence here. Okay. So you want to know, are those two things close? Are you paying for believing those two things are independent while in fact, they were dependent? So you see that the mutual information is going to come in very naturally. I mean, it's still a beautiful idea and nobody noticed it before, but in hindsight it's very natural. Okay. So the key lemma is like this. It's a decoupling argument. And it goes like this. So let f be some function from x times y to r, and xy random variable in x times. Okay. Let x bar, y bar be two mutually independent copies of xy. Be mutually independent. Okay, so x bar is independent of y bar. And they are copies of x and y. Okay, so x bar has the same distribution as x, y bar has the same distribution as y, but x bar and y bar are independent. Okay, so you see, it's exactly this situation. Okay, what we're going to take x to be h bar of s, and we're going to take y to be some z. Right? So here they are mutually independent, and here they are dependent. And for f, we're just going to be taking the loss. Okay. And now the lemma says the following. If x bar y bar is sigma squared sub-Gaussian, I'm going to explain what this means in a minute. But for the moment, take it like this. Then the difference between the expectation of f of x y and the expectation of f of x bar y bar, this is going to be bounded by square root 2 sigma squared times the mutual information between x and y. Okay, and again I'm going to explain sigma squared sub-Gaussian in a minute, but first let me tell you the immediate corollary to this. Which is immediate from this, plus the statistical discussion, plus the definition of sigma squared sub-Gaussian. The corollary is that the generalization of h bar on mu, this is upper bounded by square root of mutual information between h bar s and s over m. Okay, so now this is exactly what we wanted here. How much information of the data S is contained in h bar S. Okay, this is this mutual information term. If this mutual information is not too big, then you generalize. If you didn't memorize too much of your data, then you know you will generalize. reminder of Gaussian. So this means U is sigma squared sub Gaussian if the following inequality is true. Log of the expectation of e to the lambda u minus the expectation of u. Okay, this is known as the log Laplace transform. It's super useful everywhere in machine learning. It's kind of a control on the moments, you see. This should be bounded by, it should be the second order term, so it's going to be a lambda squared. Lambda squared, sigma squared over 2. And this should be true for all lambda in R. This is a definition of being sigma squared sub Gaussian. For instance, a Gaussian invariant sigma squared is sigma squared sub Gaussian. Similarly, if u is on an interval of length sigma squared, then it's some constant times sigma squared sub Gaussian. For example, n0 sigma squared or nu sigma squared is sigma squared sub Gaussian. If the support of u is some constant, then u is constant sigma, a constant sub Gaussian. And all the constants. Okay, so for instance, if you are bounded on the interval 0, 1, then you're sub-Gaussian. Now the key point of sub-Gaussianity is that when you're taking averages, it improves, just like when you take average of Gaussian. So if you have 1 over m, a sum of ui, where, let's say from I equals 1 to m, where ui, iid in some interval, say 0, 1, then let's call it omega, this thing, then omega is 1 over m sub Gaussian. Okay, so this is where you get this 1 over m in the square root. You get this 1 over m in this lemma from the sigma squared sub-Gaussianity. And the sub-Gaussianity is 1 over n for this application because you're going to take an average. Okay, so exercise, put together everything I have said so far. Just prove the corollary. Okay, any question on this? I'm going to move to the next topic. Yeah.
There is one question.
Yes.
It's about the notation h bar s. Is it just the image of s by h bar, or it's you have trained h bar on s?
Yeah. So I tried to be consistent, but I probably wasn't. So I want h bar. It's always defined for me as a map from a data set x, y to the m to y to the x.
Can you write on the left so you can mix it from the
Yeah. So again, h bar, oops. H bar is always from x times y to the m to y to the x. So I should write h bar s of x. Okay, that's my prediction. And if I just write h bar of x, it means that implicitly I have forgotten about the data set. Yeah, and this notation is, remember I used L of h on z. This is L of h at x compared to y. So there are many small abuse of notation which can make things a bit confusing. Okay, so another one which is somewhat related to this. Actually, I think maybe there is a deeper relation, but it has not been worked out yet. Is the PAC-Bayes analysis. It goes back to McAllister in 2003. Okay, and the proof of this, by the way, is really, really beautiful. I highly recommend it. To take a look. Okay. Oh yeah, maybe I can mention somebody else. Chu and Rajinsky. You can also check a recent paper by Chu and Rajinsky, which generalize some of the stuff that we saw in did. Okay, so the PAC-Bayes analysis. Let's do it. So I'm just going to tell you the theorem and how to interpret it. So the theorem goes like this. Let P, capital P, be prior. Doesn't matter prior. Okay, it's just for intuition the direct graph. The distribution, the prior distribution, if you want, on maps from Y to X. Okay, so this prior, this is going to be your inductive bias. So before seeing any data, you believe that there is a certain relation between input and output, which is more likely than some other relation. Okay, and you have a full grading, a full ranking of the different hypotheses. Okay, so this is your prior distribution. This is your inductive bias. Now the theorem says the following: for any Q distribution on Y to Z, and Q you should think of it as your posterior distribution. Now you're seeing some data, and you believe the world was something, but now you have some real evidence, and you have to update your beliefs. You update it to Q. This is a new distribution. So now, what you care about is you're not going to say, I have found a single map, H bar S. But now you have a distribution. So now you might care about generalization when you sample from this distribution. So what the theorem says is the following. The expectation, if you sample a map H from Q, of the generalization of H on U, S generalization. This is upper bounded with probability at least 1 minus delta by square root. Okay, so you get a log. Let me just see where the log is. You get a log m over delta over m times the relative entropy between Q and P. Okay, this is a theorem. So this tells you that if you sample from Q and you compute your empirical error, it's going to be close to the true error you will get when you sample from Q up to this term. Now what is this term? This term is saying that, okay, if you didn't update your belief at all, then you're going to generalize. Of course, because, P, you obtained it without looking at the data. P does not depend on the data. So the expectation, the generalization from P is actually 0. You do generalize perfectly when you sample from P. But if you have updated, if you have looked at your data, it depends how much did you change your mind about the state of the world. So it's like stability and robustness. So this mutual information and this relative entropy, they have a similar flavor, but they are telling a different story. Now, you can, I'm not going to do applications of those things, but you can Now you can try to use this for IBM or for many other things, and there are many resources on the net that you can look up for this. So you were saying we don't see it here?
No, it's
Just a small thing.
This one's for,
Okay, so this is it in terms of information theory. I'm not going to say any more than that. I'm now going to tell you about a completely different viewpoint, yet again, which is online learning idea. Okay, and I like online learning a lot, and one reason I like it a lot is that because we're going to prove things without making any probabilistic assumption. Okay, but in the spirit of this course, I'm going to tell you how those things that we say without probabilistic assumptions, they tell you something about the random case. Okay, so now, so it's a game, let's say. So Z1 up to Zn is a fixed sequence in Z. A fixed unknown sequence in Z. Not necessarily okay, it's any sequence. And the game goes like this. At every time step t, t from 1 to n, what you do is you predict using some ht, so hypothesis ht in H, which was obtained from all the previous data that you have seen, Z1 up to Zt minus 1. Okay, so when you are at time step t, so now we think in a sequential framework, where the data points are going to be revealed sequentially. We're at time step t, we have seen so far Z1 up to Zt minus 1, and now using this information, we're going to predict using some hypothesis ht. Once we have done that, so the loss is defined, the loss at time t is defined as L of ht on zt. So you evaluate your hypothesis on a fresh sample, on a new sample, on zt. And then you observe zt. So this is the online learning framework. The way to think about it is imagine that you have a stream of images coming at you. You have seen already some amount of data. Now you have a new image that comes, and you have to say if it's an image of a mushroom, and you have to say if it's a poisonous mushroom or not. Okay. So you see the image, you have some hypothesis, you classify, and then there is an oracle that tells you whether you were correct or not, whether you have the right prediction or not. And then you move on to the next one. So this is the online learning framework. And in that scenario, what we look at is what is called the cumulative regret. So the regret at time step n, this is your sum of losses, the total you have lost, up to n, L of dt, compared to the best you could have done in hindsight, had you known in advance the sequence of the i's. So minus, let's say, the minimum, the infimum over h in h of the sum for t equals 1 to n of L of h on dt. This is the definition of regret. Now, let me tell you what's the relation between this regret and generalization. relation between regret and generalization. And then I will show to you how you can bound this. It's not obvious a priori that this type of things can be controlled. I mean, we make no assumption, zero. So how can you do this? Okay, but first, what's the relation between those two things? Okay, let's see what's the best way to explain this. Yeah. Okay. So let me take tau to be a random time. Uniform random time. In 1 and 2. Okay. And what I'm gonna output, so now S, again S is Z1 up to Zn. Okay. And I'm assuming now this is IAD. Okay. So let's say the way you think about it is I have this data set, it's IID, and I'm going to run, to get an hypothesis, I'm going to run the online learning framework. I'm going to do an algorithm for the online learning framework. And I want to show to you that if you have a small regret, then you generalize. And to do this, the algorithm for the batch case that I'm going to take, h bar of S, I define it to be h at time tau. Okay, so this is online to batch reduction. Okay, so the batch setting is when you have your batch of you have your data available and you do something. This is h bar s. The way I'm defining a batch algorithm from an online algorithm is I say I run my online algorithm and I just take the hypothesis that I got at a random time. And now I want to show to you that this generalizes. Okay, so run shows that if the online algorithm has a small regret, then h bar generalizes. That's what I want to show. This is going to be very simple, but conceptually there is a little bit of a leap here. So let's look at L mu of h bar. Okay, so this is the expectation when z is sampled for mu. L of h bar s on z. H bar s, so if I want, I will take the expectation of a tau also. Okay, so when I take the expectation of a tau, what I get is 1 over m, the sum for t equals 1 to capital T, of the expectation and the t equals 1 to little n, sorry. The expectation when z is sampled for mu of L of h tau, t on z. Right? H bar s is h tau, so when I take the expectation with respect to tau, I just get the average like this over time. But now, here's the key. ht only depends on z1 up to zt minus 1. So if I take the expectation with respect to s, this is the same thing as L of ht on zt. Okay, so note the expectation under z of mu L of ht z. This is the same thing as the expectation under zt of L of ht z t. So when I take the expectation with respect to s of this thing, I will just get the empirical error L of ht zt. So this means the expectation under, let's say, tau and s L mu of h bar s. This is equal to the expectation over s of 1 over m, the sum for t equals 1 to capital to little m, sorry, of L of ht zt. But this is what I control from the regret. So I will exactly get that this thing is close to the best you could have done, up to a little bit. So let me just complete the argument. If I want to complete the argument, I just get the expectation and the tau and s of L mu h bar s. This is equal to the best, okay, the expectation of the minimum over s over h of the sum of 1 over m, the sum for t equals 1 to m of L of h dt, plus 1 over m is the expected regret. Okay, this is equal, so the true expected loss of my hypothesis, it is the best I could have done in hindsight plus the regret. And this thing, you can of course, again the expectation of the minimum, it's smaller than the minimum of the expectation. So this is smaller than the minimum over h in h of L mu of h. Right? Because the expectation over s of this thing is just L mu of h. So I really get that the risk, the regret of this thing is bounded by the cumulative regret. So this is the online to batch deduction. Okay, so all I'm saying is that this framework is more general than everything we have done so far. It subsumes everything else.
Is it correct that the regrets that you define on the right can be negative?
Yes.
Can this be a problem directly, or
No.
just seems
Yes. Okay. I mean, we could do unlimited number of hours talking about this, and in particular, you might want to go beyond comparing. So, if really there is a sequence, one great thing about this is you're not assuming it's I. In particular, it might be that your distribution is shifting over time. So maybe there is some seasonality in the data, and around Christmas something else happens, and you don't want to use the same predictor all year long. So then what you want to say is you don't want to compare to the best fixed guy. Maybe to some hypothesis that changes a couple of times over the year, and you can do all of this. But then it becomes a different course. Okay, so let me just explain briefly how you can hope to bound this. So, example of bounding regret. So let's see. So let's do it in the convex case. Let's do online convex optimization. Now you're predicting a weight, and I'm going to assume that the map from W to L WZ is convex and 1 Lipschitz. 1 Lipschitz in W for any x. For any z. Okay, and I want to control the regrets. That's the game. So I'm at time t, and currently I have WT. Okay, that's what I have right now. I have WT, and I use WT to do some prediction, and my loss was the loss evaluated at WT on ZT. That's how much I paid. And now I want to know what is WT plus 1. Okay, that's what I need to tell you an algorithm. You obtained this. So what you would have liked is actually, if you knew in advance you were going to be evaluated on ZT, you would have picked the W that minimizes L of WZT. Then you would get a negative regret, as you were saying. But you have to trade off between, being faithful to the new data and not changing your mind all the time. Okay, this is coming back to the stability. If you're not stable, you're not going to generalize. If whenever you see a new example, you do something completely different, then you're not stable, you're not going to generalize. So you need to trade off between being good on the new data and being stable. So one very natural idea is to do a gradient descent-like strategy. So you were here, but you wish you were going toward the minimum. So you can look at the steep direction of steepest descent, okay, which is just the gradient with respect to W, and you can do a little step in that direction. So you do WT minus eta times the gradient. Okay, and that's the algorithm. That's online gradient descent. And in this form, without assumption, it goes back to Zinkevich 2003. But of course, gradient descent itself, this is also known as stochastic gradient descent, SGD, if the ZTs are IID. And then this goes back to Robbins-Monroe. Robbins-Monroe in 1951. Okay, so stochastic gradient descent, the algorithm that everybody uses to train neural networks, is just this equation. Okay. And for neural networks, the assumption is that the ZIs are IID. Okay, so let's do the analysis of this algorithm. Regret analysis. So we care about the sum for t equals 1 to m of L of WT ZT minus L of WZ or some W. That's what we care. By convexity, this is upper bounded by the sum for t equals 1 to m of the gradient with respect to W of L at WT ZT inner product with WT minus W. This is just the definition of convexity. Convex function is above its tangent. And now we see something very nice, which is the following. If this is positive, okay, so the picture is like this. You have W and you have WT. And I'm moving in a certain direction with my gradient. This is the gradient W, LWT. Okay? I don't know where I'm moving. Okay? This direction can go anywhere. I don't know where is W. I don't know where is the best. So the point is, if this term is positive, if I do suffer regret, then it means this direction is correlated with this direction. So if I regret, then I also learn. Whenever I regret, whenever this term is positive, it means this points in this direction, in the direction of W. So if I regret, if I pay, then I also learn something. Okay. So this picture means if I regret, then I learn. And something useful to do in life in general, by the way. Okay. So mathematically, how do you do this? Well, it's you can do what's called a potential-based analysis. Which is simply looking at your distance to up. Consider the distance W minus WT. Okay, how far are you? And the point is going to be that if you pay, then this distance goes down. Whenever you pay, you get closer. Sometimes you might be going away, but if you go away, then you're not paying, so you don't care. So it goes like this. So let's look at how much this has dropped. Okay, so this is the same thing as the norm W minus WT minus W minus WT minus eta gradient of L WT. Okay, so you see when I expand the square, those two squares are going to cancel, and what I'm left with is eta squared gradient of L WT dt, norm of this, plus the inner product. Okay, there is plus 2 times the inner product. Plus 2 eta grad L WT dt inner product with W minus WT. Okay, which is exactly what we wanted. If you pay, meaning this is negative, then your distance shrunk. Okay, you got closer. This thing, because it's Lipschitz, we said 1 Lipschitz, this is bounded by 1. Okay, so what you get is exactly that grad L WT ZT inner product with WT minus W, which is an upper bound on the regret per time step. This is upper bounded. I normalize by 1 over eta. You have 1 over eta plus this thing plus your eta, sorry. You have eta plus 1 over eta, norm of the difference. W minus WT, norm squared, minus W minus WT plus 1, norm squared. So when I sum these things, what's going to happen is that I get a telescopic sum here. Okay, so the regret, after seeing m samples, is bounded by eta m plus the first term, W minus W1 squared, over eta. So if I optimize over eta, I get square root m times the difference. So you see, I get a very tiny regret. Regret can scale linearly in m, but here we see a square root m factor. So this is very good. In particular, the generalization here, right? This was the generalization term. You see now, if your regret is square root m, this becomes 1 over square root m. And you even get the radius up there, this norm. So it's, again, it recovers what we did with stability, with Rademacher. It's just another point of view, which might be more powerful in certain cases. Okay, any question on this? Okay, so now we're going to see the last generalization topic before I tell you a very brief introduction to robust machine learning and adversarial examples. So the last one is number 6. Which is margin. So we're going to revisit binary classification. Revisit binary classification. Okay, so from VC binary classification with half spaces. Okay, so from VC theory, the sample complexity is of order of t. Okay, so if you want to learn, so remember your concept, so we have maybe minus, 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 plus, 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 plus. Okay, it's like this. That's what you want to learn, and from the VC theory, you know that if you're in dimension D, you need to see a number of samples which is of order of the dimension. That we already did. Now I'm going to tell you that you can do much better if you have margin, like in this picture. So let us assume now, the data is separable. Meaning that there exists a classifier which is perfect. Okay, so that means, let me just think. There exists W star such that y x in a product with W star is strictly positive, almost sure.
With data, do you mean S or mu in this case?
Here I mean let's do it on the data, on the aggregate data, and let's see if that's enough. So for all I. So in particular, because it's a finite set, there is a minimum value, which is strictly positive. Okay, so this is equivalent to saying there exists W star such that yi xi W star, W star, is bigger or equal to 1 for all. Okay, I can just rescale my W star such that this is true. But now the picture is like this. Okay, so this is the hyperplane W star dot x equals 0. Here I have strictly positive, here I have strictly negative. I know that this line is W star dot x equal to 1. I can rescale so that, you know, the closest example, it's a 1. So what is this distance? This distance is, okay, so see the picture is, this is W star. I don't know what is its magnitude, okay. But how far can I go if I want to be on the hyperplane such that W star dot x is equal to 1? Well, W star dot W star over the norm of W star squared, this is equal to 1. So this distance is 1 over the norm. The margin, geometric margin, is exactly 1 over the norm of W. So if I assume that I have a lower bound on the margin, I have an upper bound on the norm. so margin at least 1 over at least gamma implies norm of W star is at most 1 over gamma. This leads to a natural algorithm now. I have this data set and I'm trying to find a hyperplane. There are many hyperplanes that are going to classify correctly. Which one do I pick? Well, I'm going to pick the one which has the smallest Euclidean norm. It's a natural algorithm. Is to minimize the Euclidean norm of W, let's say square, subject to yi xi dot W is bigger or equal to 1 for all I in 1 to 1. Okay, and this is again a convex problem, so you can solve it efficiently. And this is the SVM algorithm. This is the SVM, support vector matching. And the support vectors are the examples that sit, tight, that make this inequality tight. And now we see that when we are searching over this, effectively, we know that we're never going to output a W which has an L2 norm more than 1 over gamma, because we know that op has an L2 norm at most 1 over gamma. So we can use Rademacher complexity bounds that is going to tell us that the generalization of this is at most 1 over gamma times 1 over square root. Okay, so from 2, we find that L mu of SVM. Okay, so we want to use Rademacher bounds, okay, on W. So we need some kind of, we want to use a contraction lemma, so we need some kind of Lipschitz loss. One way to use a Lipschitz loss is remember the hinge loss. Remember, you have the 0,1 loss, and you have the hinge loss. The hinge loss is 0 if you have confidence at least 1, if the inner product is at least 1. So we know that L mu of SVM is bounded by L mu, let's say for 0,1 loss, is bounded by L mu of hinge loss. And we know, this is just true because of the upper bound, but now from Rademacher complexity and contraction lemma, we know that this is bounded by L mu hat M of hinge loss. Of SVM. Plus the Rademacher bound, which in this case, we know it's 1 over gamma squared, so we get constant over gamma square root M. This is Rademacher plus contraction lemma. Not we're going to redo it. But this thing is 0. This thing is 0. Right? The empirical loss of SVM with the hinge loss, it's 0 because I classify all of my things correctly with confidence 1. So we now see that the sample complexity is not dimension, but it's 1 over gamma squared. Sample complexity is 1 over gamma squared. Okay, which can be much smaller than the dimension. And totally unrelated to the dimension. But you see, this sample complexity parameter, it's distribution dependent. whereas the VC dimension is distribution independent. So with VC, you don't have to think about what is your distribution, whether it has margin or not, but what you lose is you get a very pessimistic bound. Okay, any question on this? I know it went fast, but I guarantee you I told you everything to understand this tool. Yes?
So now if we scale down all the data by some factor,
Yeah. So I'm assuming the norm is bounded by 1, right?
the norm
Of the x's.
okay.
Yes. Otherwise, you always need some normalization. So I think I said it at the beginning of chapter 3, which is I'm going to assume the norm of x is bounded by 1, and the value of L is into 0, 1. Yeah. Otherwise, yeah, you can always go very scale. But still, maybe your question is still valid, I don't know. Okay, let me just say one thing about non-separable data, and then we move to robust ML. So, non-separable data. The first thing to know is that you cannot find computationally the hyperplane that minimizes the number of mistakes. Okay, so let's say we have some plus here and some minus like this. I don't know. Finding the best hyperplane is computationally hard. So finding the hyperplane minimizes the number of misclassifications. Or in other words, that minimizes the empirical loss with the 0-1 loss. This is NP. Okay. So you cannot do it. Just cannot do it computationally. Which is why logistic regression and SVM are so useful, because they do give you a convex upper bound on this 0-1 loss. So minimizing the hinge loss or minimizing the logistic loss, this is doable. Okay, and SVM is just minimizing L mu hat M with the hinge loss plus some regularization. Okay, and now you have seen by now 5 ways to analyze this. Okay, we already did it with stability. You can redo it now with margin. Okay, there are many ways to do it. I'm not going to redo it, but this is how you deal with non-separable data, because you cannot. It's not computationally feasible to find really the best, the one that minimizes the number of mistakes. Okay. Now let's move on to the last chapter, which will have to be brief. Brief introduction to robust ML. So what do I mean by robust? So far, we assumed that x, y at test time has the same distribution as xi, yi in the data set. otherwise, what could you do? I mean, if the distributions are completely different, if you have been trained for some question and then you ask the question which has nothing to do with it, how is your training relative? So it seems like a natural assumption. However, this assumption is violated, I think, in all machine learning applications to various extents. And it's not clear at all that what we have talked about so far remains valid even when there is a small discrepancy between test time and training time. So let me see what order I will do. So let me tell you first an example of why this is an issue. How things can go wrong. Okay, they can go wrong in many, many ways, but let's do the following. So say y is sampled from -1, 1 uniformly. Okay, so a priori the output is just a random output. And now what is x? X is going to be related to y in some way. So x is just going to be x1, x2. There will only be two coordinates. And the coordinates are going to be like this. x1 is going to be epsilon y, or some epsilon. So in the first coordinate, you actually read the output. You know what is the output. And x2 is going to be y with probability, say, 0.9, and minus y with probability 0.1. Is the example clear? It's a very simple two-dimensional example. You have two features, one output. The output is, completely correlated with the first features, and it's only a little bit correlated with the second feature.
So what is the epsilon?
Yeah, epsilon is some small number. So for now on, fix epsilon tiny. This is the amount of robustness you will want. It's 0.001, something tiny. So in this example, what is a perfect accuracy classifier? Can you give me a linear classifier which is perfect? Sine of x1. Right? This is the only perfect linear classifier. So perfect linear classifier is the sine of x1. But now what if at test time there is a very tiny perturbation of the distribution, an epsilon perturbation. But this epsilon perturbation erases the first features. So have epsilon y, but now it's going to be 0. But a tiny epsilon perturbation at test time makes this, so perfect linear classifier, 100% accuracy. It's just perfect. But now an epsilon perturbation at test time makes this a 0% accuracy classifier. It was perfect, but it was using a feature which is really non-robust. Very, very non-robust. The right thing to do, of course, was to use the sign of x2, because x2 is robust. The correct robust classifier use x2. And you can do many variations around this example. You know, maybe you don't like the fact that this has a tiny value, and you would have liked me to show you an example where you have features of reasonable values, yet they are not non-robust. It's easy to do. I could cook up one for you. You can see for that Tsipras et al. This is from I don't know, a couple of days ago or a couple of weeks. I don't remember. See also the paper in the Madrid lab. If you look at this, you will find it. Okay, but you see the point. The point is that if you train without having robustness in mind, things are going to go horribly wrong. Okay, and it's not a mathematical problem, it's a real problem. It's a very real problem. Okay, so I will tell you briefly two other things. One is a paper that I really like, which is called Nightmare at Test Time. This is from Gloverson and Sam Robright from 2005. So what those guys cared about was robustness to deletion of features. So again, deletions of features, it's something that can really happen for real. I mean, imagine, you know, you have collected your data, and then at training time something happens, and you have a user that comes, and the user didn't fill in whether he was a male or female. But your classifier, somehow it was using that information crucially. Now that this information is missing, you're dead. You're not doing a good job. Okay, so you really, robustness to deletion is like super important. So what they proposed the modification of SVM. So modification of SVM to be robust to feature deletion. Of course, it should be limited feature deletion. Oh, and another point I wanted to make with this is that this guy, the sign of x1 was perfect classified. But if you wanted something robust, you had to diminish your accuracy. Okay, so from 100% accuracy, you got to 90% accuracy, even without noise. Okay, so if you want something robust, you might have to settle on something which is not as good as a non-robust classifier, even if there was no adversary, no noise. Okay, so the same thing here is true. If you want something robust, and you wanted it to be robust to any feature deletion, then okay, there's nothing you can do. But let's say you have limited feature deletion. So what they propose is to minimize the following modification of the hinge loss. So let's call it L adversarial hinge loss. It's going to be the following. So let's say you put W and the test on XY. So you remember the hinge loss is just the positive part of 1 minus y x dot w. This is what the hinge loss is. This picture. So now what those guys said is, okay, let's look at what happens if there is an adversary that can delete some of the w's. So let's look at how much pain it can cause us. So let's maximize over all alpha in RD. Let's say alpha in 0, 1 to the d. Such that the sum of the alpha I is at most k. Okay, so alpha I tells you if you delete a feature or not. And you want to have a certain amount of deletion. If you delete feature I, then this should be put to 0. So it's this with the Adama product with 1 minus alpha. Okay, Adama product just means entry-wise product. Okay, so whenever alpha is 1, I put this coordinate to 0. And the point is, exercise shows that this remains a convex problem. Okay, so this is what the paper is about. I mean, it's just a few lines, it's easy. But the point is, for SVM, you can put this type of restriction and you will still get a convex problem, so you can efficiently find the solution. And again, the solution you will find, in this example, it will give you x2 instead of giving you x1. So it will give you something with slightly less accuracy, but which will be robust to feature division.
So if I understand correctly,
Yeah.
we assume that at maximum k
Yes.
features will be deleted, and then we're maximizing the worst case.
Yes. You're saying, okay, what would be the worst features to be deleted? But look, I mean, it's easy to see what would be the worst features. It's those that are the most correlated with yx. And then once you have this formula, you plug it in, and okay, you will find that it's convex. But yes, that's what this is doing. Yeah.
Why don't you learn on data installation? I mean, you have the data installation and...
Yeah, okay. So, say I'm going to delete k things out of d. Well, I have d choose k possibilities. So I'm in trouble. Yeah. Which is the main point of all of this. The point is, it's a computational issue. So the last theorem that I want to tell you is about some work that I did recently, which is exactly trying to say that the main issue of robust machine learning is not an information theoretic issue. So far we have mostly been talking about information theoretic. Here it's not an information theoretic issue, it's really a computational issue. Okay, so let me tell you the last theorem. Some bad news. Okay, so here is a theorem. This is myself, Eric Price, and Ilya Rasenstein from a couple of weeks ago. So again, we fix epsilon and m. Think of epsilon as tiny and m as very large. There exists a classification task, a binary classification. Binary classification task such that the following is I'm just thinking at what level of details I want to give it. So it is learnable with SVM. O of these samples. Okay, so it's not a crazy, a priori it's not something crazy. Okay, it's some classification task where SVM is going to do a perfect job with just a small number of samples using everything that we have been talking about. It is robustly learnable with perturbations of size m. Okay, and for scaling, because it's an important question, the size of the example is up to some log factor of square root d. Okay, so m is something large. Okay, you're in some ball of radius square root d, and you can do large perturbation of size m. And you can learn there exists a classifier. It's not like it doesn't exist. It exists. There exists a classifier which is robust to big perturbations. So just like here, there is a 90% accuracy classifier which is robust up to perturbation of size 1. So in this example, there exists a classifier which is robust up to this big perturbation. And it's getting, 100% accuracy. When I say this, I say nothing about computation. It's robustly learnable with an exponential time algorithm. Okay. It's robustly learnable with exponential time. Or potentially exponential time. Okay, we don't know how to show that you can learn it with a polytime algorithm. And now the punchline is the third point. It is not computationally efficiently learnable, even with perturbations of size epsilon. So there exists a very robust classifier, yet you cannot even find one which is even a tiny bit robust. Even a little bit of robustness, that's too much to ask for computation. So of course, I don't know what's your background in the audience about computational complexity, but saying that it's not computational, that something is not computationally feasible, we don't know how to prove those things, so you need to rest on some assumptions. I just told you one which was NP hardness. This cannot be NP hardness because it's about an average case result. So we don't have an average case theory of NP hardness. So we need some other kind of assumption. And what this is to be more precise, this is statistical query hardness. I will just conclude with this. But before I explain what is statistical query hardness, is the statement clear? What I'm trying to convey. So there is some classification task which in principle you can learn even with big perturbations, but actually finding it computationally, even for very tiny perturbations, you cannot do it. Okay, so this is very bad news for robust machine learning. But it's not the end of the story, of course, because the truth of the matter is that this classification task probably doesn't look like anything like the distribution on real images, say. Okay, so the hope, what the next step is can you say that for certain distributions you can do robust machine learning? In particular, can you do it for real life distributions? It's difficult. Okay, so what is statistical query? So in statistical learning theory, we have xi, yi, sampled from u to z. Okay, that's our data set. You can do whatever you want with it. In statistical query, you have an oracle that does the following. So you ask psi, which is a map from pairs input-output to a real number. Okay. So you can ask a function. This is your question. For instance, you can ask, okay, you can give as a function your hypothesis, and you can ask how good is it. And what the oracle answers with the expectation under xy from mu of psi. So it tells you what is the expected value of your thing, plus a little bit, plus some psi, where psi, the norm of psi, the absolute value of psi, is less than tau. And this is the precision. Precision of the oracle. So if you have a polynomial precision oracle, you can simulate a polynomial precision oracle with a data set of polynomial size. Okay, so that's a statistical query model. All algorithms we have seen, you can implement them in the statistical query model, except for nearest neighbor. Nearest neighbor is not a statistical query algorithm. And what statistical query hardness tells you is you need exponential number of queries even to an exponential precision oracle. Okay, so even if you have an exponential precision oracle, which you cannot have with polynomial number of samples, but let's say you have an exponential precision oracle, I'm being generous with you. Even if you have this, you still need an exponential number of queries if you want to find something robust even to tiny populations. Yeah?
So when you say robust with perturbations of size
Yeah.
epsilon or n, it means that if I take the x, I add a random perturbation of size,
Not random.
or well, some perturbation
Perturbation, yes.
of norm less than epsilon,
Yeah.
it will still give the same answer.
It will give a different answer. No, robust means it will give the same answer. Yes. Non-robust means it will give a different answer. And here I'm being vague with the norm because it doesn't matter if it's L2 or infinity or it's basically true for any norm. So that's why I'm being vague. Okay, that's all I wanted to say. Thanks.